Hello, Physics 2. So we are on part 2 of Monday's lecture, continuing on with Faraday's law. So we had been talking about how whenever you have a time-varying magnetic field, you get that non-Coulomb electric field. And so we had just talked about the different directions, and now we're going to start building this into some really cool physics applications. All right, so if we have an electric field, then you can use this to think about driving currents. So remember chapter 18 where we went through such excruciating detail on exactly how to think about a current in terms of an electric field driving the electrons around? Well, now you're seeing why we did this. So now we really get the fun payoff of all of that conceptual practice. So let's go back to the solenoid, which is really going to be our best friend in this chapter. So we have a solenoid, we have a time-varying magnetic field, so thus we would have an electric field being produced around it. And so what if in this time-varying field around the solenoid, so we've got B increasing, what if we placed a circular conducting ring around the solenoid? What would happen to it? So we know that there's an electric field that is around this solenoid, so there is an ENC going around, and this electric field will drive a current in this ring. So the ENC drives current in the ring. And this works just as well as a battery. So this is a really powerful application of Faraday's law and what power you can harness with a time-varying magnetic field. So we would then, building on what we know about this magnetic field and its relationship to this electric field that it's generating, it would make sense that the current in the ring is proportional to the electric field induced by this time-varying magnetic field. So, and all of this goes perfectly in line with our previous discussions on current and circuits and the relationship between current and electric field. Okay, so let's draw some pictures. So essentially, we're going to start off, we've got our magnetic field. We would have the current in the solenoid. Then you would have the distance at which you were going to place your ring, so you'd have some related non-Coulomb electric field. So you could place a ring here and get a current that would be related to this electric field. And we'd have our B inside increasing in time. So here we have a side view of the induced current. You can see how the curly electric field could be used to drive current around a metal ring. So as long as you've got that constant electric field, you're going to get those electrons moving. Of course, if you were driving electron current, it would go in the opposite direction as that curly electric field, and whole current would go in the same direction as the electric field. Okay, so moving on, if you recall, EMF is the non-Coulomb energy per input charge. So remember, it's not electromagnetic or electromotor force. It is non-Coulomb energy per input charge. I know, it's another misnomer. And so the force per unit charge is ENC, which we've just talked about. So we can use this to go after EMF. So EMF is equal to the path integral, let's get that through that little circle there, ENC dot DL is equal to, in the case of the ring, it would be ENC 2 pi R2 for above diagram. So in this case, we would place a conducting ring. And so if you go around that, then you would see that would just be 2 pi r. So make sure that if you haven't brushed up on your perimeters of different shapes, that you have those geometric formulas at your disposal. Okay, so building on that, so we already have some expressions to relate EMF to current. So the current in the ring is I is equal to EMF over R, where R is the resistance of the ring. So this really does just look like a battery in terms of how it's working. Okay, so let's take this apart a little bit more. So what if we doubled R, the radius of the conducting ring? Well, we would get 1/2 E because of the 1 over R dependence that we talked about last time. So ENC 2 pi R2 would become 1/2 ENC 2 pi 2 R2. So EMF is the same no matter what. So the EMF generated would be the same, but it would scale according, or the field is what's being scaled. So if you were to have it further apart, that would scale accordingly. But you would see that it would scale in a way that your EMF value is still the same. Okay, and this gives us some really interesting further insight. So EMF is the same no matter the shape. Of the circuit. So it doesn't matter if we would put a square or a triangle around it, we're going to generate the same EMF no matter what. All right, so all of this is of course building us into Faraday's law. Okay, so we can determine the direction of ENC. We know how to do that. We have those diagrams. So how do we get the magnitude? We haven't talked about how to do that yet. So far, we know that it is proportional to the rate of change of the magnetic field. And we know dp dt non-zero drives a current, drives I, and I is proportional to ENC. So we have what we need to start going after, the magnitude of what ENC is. Okay, so let's do a little pretend experiment, since these days I think all we're doing is pretend experiments. So we've got our solenoid, and we have an ammeter, minus plus, and it's going around. So we can measure the current using the ammeter. So ammeter going around a solenoid with I, and it's measuring the induced I2. So this is the current that's driving that time-varying magnetic field, and this is the current that has been induced by the time-varying magnetic field. All right, so we know the resistance of our new circuit. And we know EMF induced acts like a battery. Okay, so as I stated before, but I'm going to write out explicitly. So we vary I1 in the solenoid, which is going to give us dB dt non-zero. Okay, so let's look at a couple circumstances. So let's say I1 is increasing. So then dB dt is increasing. Thus, I2 is not zero, and the ammeter will read negative. Okay, so we also know there is a curly non-Coulomb electric field. Okay, so let's look at, so that would be the case of having the increasing current inside the solenoid, making an increasing time-varying magnetic field, of course generating a non-zero current in the ring around it that would be negative, that would correspond to the direction of the curly non-Coulomb electric field. Okay, so let's look at the next case. This one's a nice easy one. So let's say I1 is constant. In this case, then dB dt is zero, or constant. Then I2 is zero, and you have no curly non-Coulomb electric field. Unsurprising, we've already discussed that reality. Now let's say I1 is decreasing. Thus, the time varying magnetic field is non-zero and also decreasing. So let's say it's at half the initial rate. Then I2 is also non-zero, and the ammeter will read a positive, and you'll get a reading that was 1/2 the initial. So we see that the non-Coulomb electric field and EMF are both proportional to dB dt. Again, unsurprising. All right, and then let's say we had a solenoid with twice the area, same magnetic field, and this results in twice the current generated. So what we get from this is that EMF, or the magnitude of EMF, is equal to d dt B1 pi R1 squared. And this portion is magnetic flux. Written as phi mag. I've also seen it written like this as well. And this is, okay, so building on that, then on the area encompassed by the circuit, you have that the magnetic flux on delta A is B dot n hat delta A, which is equal to B perpendicular delta A. So this looks a lot like our formulation for electric flux. Now we'll formally define magnetic flux. So magnetic flux defined is equal to B dot n hat dA is equal to B perpendicular dA. Very similar to Gauss's law. Okay, so let's do an example. Say we had a triangle with a base of 0.7 meters and a height of 0.4 meters. And then we have a uniform B of 0.86 Tesla points away from the perpendicular plane of the triangle loop of wire. And what we want to know is, what is the magnetic flux? Okay, so here we've got our 42 degrees. Here's our magnetic field. There's the perpendicular. This is a loop of wire. So let's calculate the magnetic flux. So the magnetic flux is equal to B perpendicular dA, which is B 1/2, so remember it's 1/2 base times height, 0.7 meters times 0.4 meters times cosine of 42 degrees. So we just have that formulation for the dot product. So our magnetic flux is just 0.089 Tesla meters squared. And of course we subbed in the 0.86 Tesla into B, generating our final result. Okay, so moving on. So this relationship of the time-varying magnetic field to the induced EMF was discovered by Michael Faraday. Very interesting physicist. I highly recommend reading more about his life. And so we denote this as Faraday's law. EMF is equal to the change of magnetic flux dt, where EMF is equal to the path integral of the non-Coulomb electric field dot dl, which is the path around. And so we get, and magnetic flux is also equal to minus B dot n hat dA. So, in words, the EMF along a round-trip path is equal to the rate of change of the magnetic flux on the area enclosed by the path. So, and if you recall, the direction of ENC, point your thumb toward minus dB dt and curl your fingers. So you want to see in what direction is the magnetic field changing, and then that determines the direction of your curly electric field. So it's different than the electric field being determined by the direction of the magnetic field. It is the direction of the rate of change with respect to time. Okay, so moving right along. So you can also say that ENC.dl is equal to minus ddt times B dot n hat dA. So I wanted to take a quick moment for those of you in the algebra class. I know I have been writing a lot of calculus terminology throughout this lecture. What I want you to really focus on is that when I talk about the time-based derivative, I'm just talking about whether or not that magnetic field is changing with respect to time. And in terms of these surface integrals and path integrals, we're going to be looking at particular geometric situations where you can easily calculate that surface area or that path. So you're not actually going to be doing any calculus in this section. So pay a lot of attention to how we approach these, the example problems. I do want to see the integral formulas when you are setting up your problems. And the reason for that is they're more correct. And so I think it's important just to preserve the correctness of these expressions and to understand that what we're doing with these integrals is we're doing a sum. What we're doing with these derivatives is we're looking at something changing. But recognize the actual mathematical operations is not something that if you're in the algebra class that I would expect you to need to do in any metric where you would be graded. Okay, so we can put all this together and complete Maxwell's equations for Faraday. We're not all the way done yet. So let's complete Maxwell's equations for Faraday. So the complete expression is E non-Coulomb dot dl is equal to minus the time varying derivative of B dot n hat dA. So, and what we can see from this, bigger EMF implies faster dB dt, and bigger area implies bigger EMF. Okay, so let's do an example. And really pay attention to how we set these problems up and how we work through the steps to do this example. So we have a square loop of wire with sides, SIDE, L is equal to 5.0 centimeters in a uniform B field, where B is equal to 0.16 Tesla. What is the magnetic flux in the loop when A, B is perpendicular to the face of the loop, B, when B is at an angle of 30 degrees to the area. So think back to Gauss's law for that area vector. And what, part C, is the average I, or current, in the loop if it has a radius, or sorry, a resistance of 0.012 ohms and is rotated from B to A in 0.14 seconds. Okay, so it's going to be going through an angle of rotation, which is going to be giving it that time varying field. Alrighty, so for part A, B is perpendicular to the coils. To the coil's face, and thus it's going to be parallel to A. So the magnetic flux is equal to B dot A is equal to BA cosine 0 degrees is equal to 0.16 Tesla times 0.05 meters times 0.05 meters times 1. And so we get 4.0 times 10 to the minus 4 Tesla meters squared for our magnetic flux. All right. So moving on to part B. Did I show that? The angle between B and A is 30 degrees. So then the magnetic flux would be B dot A, which is equal to BA cosine theta is equal to 0.16 Tesla times 0.05 meters times 0.05 meters times cosine of 30 degrees. And this magnetic flux is equal to 3.5 times 10 to the minus 4 Tesla meters squared. Okay, so part C, EMF is equal to dB, or the change of magnetic flux with respect to time, which is the same thing as thinking about delta magnetic flux over delta T, and we have calculated two magnetic fluxes. So here is part A, here is part B, and we have been given a time in the problem. So the time in the problem here is 0.14 seconds. So we have the change in magnetic flux, we have the change in time, so we actually have a really simple algebraic plug and chug. So the change of magnetic flux with respect to the change in time is equal to 4.0 times 10 to the minus 4 Tesla meters squared minus 3.5 times 10 to the minus 4 Tesla meters squared over 0.14 seconds. EMF is equal to 3.6 times 10 to the minus 4 volts. And if you recall, so what we're after is current. Current is equal to EMF over R, and we were given the resistance in the problem. So 0.012 ohms. So this is equal to 3.6 times 10 to the minus 4 volts over 0.012 ohms. The current is 0.030 amps, or 30 milliamps. And there you have it. There's an example using the concepts in Faraday's law. So we will stop Monday's lecture here. We'll pick up next time for Wednesday's lecture, the last lecture prior to your exam, with some additional examples and Faraday's law, and we're going to continue to build upon these concepts.